All right, guys, good morning. So what we're going to be doing today is trying to finish up the stuff from chapter 10. We're most of the way done at this point, so yay us. At this point, what we've established is that there is an equivalency between everything we've learned using conventional mechanics for translational motion and everything that we're doing here with rotational motion. Ooh, hang on a sec. Give me a second. All right, there we go. Sorry. So, versions of everything we've seen up until now using rotational motion. We've got situations where we've had rotational kinetic energy, and we've been able to solve kinetic energy problems using that process. We've seen things that were very much like chapter 4 problems, where you had a bunch of forces and things would accelerate, only now they're accelerating in an angular sense. What we haven't talked about yet is this concept of angular momentum. And it's going to be important because angular momentum is perhaps the concept from this class that you are most likely to see again later if you move on to higher level courses in chemistry. In fact, a couple of years ago, Dr. Coolbaugh, walked into my office and he gave me this sort of stern look, and he's like, "Do you guys not ever talk about angular momentum?" Because he was getting students in physical chemistry where it's a really, really important concept, who, when he mentioned angular momentum, they gave him that kind of blank-eyed stare. I have no idea what you're talking about. And he seemed really surprised by that because he thought, man, it should definitely be a thing that the students end up covering in physics. So at the time, I had to assure him, yes, absolutely, they did learn about angular momentum. I remember that they did it. And this semester, I'm going to have physical evidence because I'm going to have this video. And at some point, Dr. Coolbaugh is going to ask me, why don't my students know about angular momentum? And I'm going to tell him, they do. Here's the proof. We did it. So if you take PChem, you can definitely recall they're going to know this stuff. So what's going to happen with angular momentum is that just like linear momentum, P from chapter 8, angular momentum is going to be a conserved quantity. You can start off with a certain amount, and as long as there are no external torques, just like back in chapter 8, as long as there were no external forces, the angular momentum that you start with is going to be the same as the angular momentum that you finish with. And that suggests an equation. So, ooh, that's cool. That was not there before. How do we? Okay, so if you don't plug in the camera will not turn on. Man, I am just not on top of things this morning. All right, can you guys still hear me? I hope so. So switch camera. Yay, there we go. All right, so the other day we learned that angular momentum, just like linear momentum, P, if P is m times v, angular momentum, which for historical reasons we're going to use L for angular momentum, is just going to be the rotational equivalent of m, that's I, times the rotational equivalent of velocity, which is the angular velocity, omega. It's not a W, it's an omega. And this is going to be a conserved quantity. So if I have a situation where an object's under the influence of no external torques, I could write a conservation equation. I could say that I initial, omega initial for an object has to equal I final
omega final for that same object. Now, how would this ever come into play? How would I ever end up making use of this? Well, one way that you might make use of it, if you think about, you ever watch figure skating, like during the Olympics or something? And what's going to happen is, a lot of times during those figure skating routines, you'll see the figure skater, they'll go into a little spin. And what you'll often see that they'll do is, when they start the spin, they're spinning relatively slowly, right? They're spinning around at a small rate of speed, and usually when they start the entire thing, you know, they go in there, their arms are open wide to the audience in a dramatic fashion. They often will have their back legs sort of trailing behind them majestically, and the spin begins and they're rotating slowly. But then what happens is, as the spin progresses, their arms get drawn in. Usually they'll fold them across their chest. Their back leg that was dragging behind them, they'll draw that in as well. And the reason that's important is because if you're in that original pose, here's my poorly animated stick figure skater. What's going to happen is, your moment of inertia, I, remember, for a point mass, was mr squared, where r is the distance from the mass in question to your axis of rotation. Well, for a non-point mass, calculating I is complicated, but conceptually understanding how it works is not. So what's going to happen is, if you're this skater, you have an axis of rotation. They're spinning around that axis. The mass in their arms and leg, they're very far from the axis. So the R for that part of their body is quite large. And what that means is that the moment of inertia is big. Now, later on in the spin, what's going to happen is, they've drawn their arms in. So here's the skater. Their legs are tucked in. Their arms are close to their body. And now what's going to happen? Apparently their head is enormous. They're spinning around an axis that is like that. But what's going to happen is, because in this case, none of their mass is very far from that axis of rotation. The result of that is that the moment of inertia is considerably smaller. However, if I started out big and got smaller, the only way this equation can stay true is if the angular velocity that they started with, so here, omega is small. The only way the equation can stay true when the moment of inertia gets smaller is if the angular velocity increases. So as they draw their arms and legs in, you'll see them spinning what eventually seems to be impossibly fast, right? That's what's happening, right? They're starting off with a certain amount of angular momentum, and as they draw their arms and legs in, the angular momentum stays the same, but because I get smaller, omega has to get larger. And you could solve problems like this. You could solve, all sorts of issues. Obviously getting a value for I for this scalar problem is difficult, because doing the calculus to figure out the actual value of I is tough, right? I can't do that problem. All I can do is say conceptually that it should be bigger here and smaller here. But you could also do things like let's call it a rotational collision problem. So let's imagine that I've got a spinning disk. here is a second different size spinning disk. But what's going to happen is those two disks, they're spinning at different speeds. So let's imagine that the left disk has an angular velocity, I'm going to call that omega 1 initial, of, let's say, 2 radians per second. But this guy over here, he's got an initial angular velocity, omega 2 initial, of something smaller. Let's go with 1 radian per second. Now, let's think about I for a second. I know that for a rotating disk, the moment of inertia is a little different from that of a point mass. It's not mr squared, it's 1/2 mr squared, right? How do I know it's 1/2? I did the calculus. How do you know it's 1/2? There's a chart in your book. Look it up. So what's going to happen is in a problem like this, if both of these objects are originally spinning, then the total angular momentum that I'm going to get for these two objects prior to the collision is going to be the angular momentum of object 1 plus the angular momentum of object 2. That's how much I started with. And of course, this is going to be my initial, because this is the pre-collision part for both of those.
Wait, what does that say up at the top?
Here,
Yes.
I'm saying that the angular velocity of this initially, so omega 1 initial, is equal to 2 radians per second. Got it? Yes, I got it. I totally did. Yay. Okay. So what's going to happen is I want these two objects to both be spinning at different rates, but they're going to come together and lock into place. They're going to end up spinning together. And why would I do this problem? Well, if any of you guys drive a stick shift, or even if you don't do an automatic transmission, this is kind of what happens every time you change gears in your car. Because what's going to happen is you've got your engine that revs with a certain number of RPM. So maybe that's this disc. And when your clutch changes gears, what happens is you're taking the spinning disc from your engine and you're going to connect that to the spinning disc for your drivetrain, the parts that actually move your wheels. And so when those two things lock together, they're going to start spinning at the same speed, right? That's why if those two velocities are too different, you'll end up getting that horrible grinding gear noise. It's a little bit different. When they lock in together, it'll speed one up and slow one down so the two speeds match. And that's what's happening here. So these two objects are going to lock together, and after the collision, they're both going to be stuck together. They're both going to have some final angular velocity, and we don't know what it's going to be. So that means that afterward, I'm going to have L1 final plus L2 final, but the angular momentum of both of them before should equal the angular momentum of both of them after. And all I've got to do is start filling in blanks. Well, what's going to happen is, let's make some masses up. Let's say that mass 1, this guy looks bigger. Let's say that he's 4 kilograms. And mass 2 looks a lot smaller. So I'm going to say that it's got a mass of 1 kilogram. And let's go with radius 1. So R1, I'm going to have that be, I don't know, let's say 20 centimeters or 0.2 meters. And the other guy looks to be about half as big. So let's have that be 0.1 meters. So now when I go to fill in this little skeleton, for L1 initial, it's going to be the I for object 1. So it's going to be 1/2 times mass 1 times R1 squared times omega, because remember I is, or L is I times omega. This is I. Omega is omega 1 initial. Then I've got to add L2 initial. That's going to be 1/2 mass 2 times R2 squared times omega 2 initial. So this is just this expression expanded out a little bit. When I do L1 final, well, what's going to happen is I'll have 1/2 mass 1 is still the same as it was, R1 is still the same as it was, but now it's going to be going at a speed of omega final plus 1/2 m2 r2 squared omega final. Of course, I realize that since this omega and that omega are the same, I can just factor that out and write it as, well, look, the 1/2s are the same, I can factor that out. The omega finals are the same, I can factor that out. So in here, I'm going to have m1 r1 squared plus m2 r2 squared. So at that point, it's really all over except for the final bit of algebra. I'm solving for the final angular velocity. I want to know how fast they'll be spinning together. So when I solve for that, I'm just going to, first I notice that everything has a 1/2 in it, so all these 1/2s conveniently cancel for me. And this is going to be ditto. I don't want to write it over again, you get the idea. So I'm going to have m1 r1 squared omega 1 initial, not squared, hello, plus m2 r2 squared times omega 2 initial, and all of that is going to be over all this garbage. Just in case anybody's wondering, no, this stuff will not cancel that stuff. That's bad algebra. Don't do it. Every year I see somebody in an exam do something like that. So now I can just plug in my numbers. So M1 was 4.
Wait, you said what doesn't cancel?
Well, a lot of times people will say, oh, look, this has M1 R1 squared on the top. This has M1 R1 squared on the bottom. And they think, oh, this cancels. It doesn't work that way. If you don't believe me, if you have 3 plus 5 divided by, I don't know, 3 plus 2, you realize the answer to that is going to be 8 over 5, right? That should be 8/5. That's the correct answer. But if you think, oh, I got a 3 on top and a 3 on the bottom, haha, cancels, it makes that 1. Well, then I would get 6 over 3, which is not the same as 8 over 5. So if you try to cancel those terms, you get the wrong answer. It's more obvious when I do it with numbers than it is when I do it with letters. And so sometimes students lose the big picture when they do that. So 0.2, and we said that this guy here was 2, this guy here was 1, 0.1, this guy here was 1. So when I crunch all those numbers, I'm going to have 8 times 0.2, sorry, 8 times 0.04, yeah. So this is 0.32 plus, this is 0.01. So the entire numerator is 0.33. Then on the bottom, I'm going to have 4 times 0.04 plus, what's the mass 1? It's 1 times 0.01. So it's 0.0, or is it 0.17 on the bottom And so the answer is that these guys end up traveling at 1.94 radians per second. Notice it's a little bit slower than this guy was going originally, but it's also faster than this guy was going originally. Why is this number so much closer to the original 2 and further away from the 1? Any ideas? Because it makes sense that if I got one guy spinning fast and one guy spinning slow, when they lock together, it certainly makes sense that my final speed should be slower than this guy because he's going to hit and get slowed down, but faster than this guy because he's going to hit and get sped up. So it makes sense that they should meet somewhere at a speed somewhere in the middle, but it might be a little counterintuitive that the number that I get is very, very close to this guy, but pretty different from this guy. So why did it not meet halfway in the middle at, say, 1.5, which is halfway between 1 and 2, but instead got almost all the way up to 2? Any ideas?
Is it because of their weight?
Close. It's not their weight. It's their rotational inertia. Because the rotational inertia, I, is different for these two objects. And you can kind of think about, like, what does rotational inertia mean? Max, shut up, dude. Thank you. Stupid dog. Never get a dachshund. So what's going to happen is rotational inertia is a measure of how difficult it is to make a thing rotate. So what's going to happen is this guy here has a rotational inertia of, well, it's going to be 1/2 times 1 times 0.1 squared. Whereas this is going to be 1/2 times 4 times 0.2 squared. This guy's going to have a way bigger rotational inertia than this guy. And so what it means is that whatever torque speeds this guy up, it's going to affect his motion much more strongly. It's going to speed him up more easily than it can slow him down. And that's why his velocity didn't change nearly as much as this guy's velocity. So we now know how to do angular momentum conservation problems. Yay! So let's make it more complicated. So what I want to imagine, you ever see one of those carnival games where you put a person in a dunking booth, right? And people like throw baseball at a target, and if you hit the target, the person gets knocked into the water, and if you don't hit the target, they sit there and taunt you, right? How does that work? Well, usually what happens is you've got a target, and I'm going to draw that target from above. So here's kind of my little target guy, and usually it's on like a little stick, and the stick is on a swivel. And what happens is the baseball, when you throw it, comes in with some velocity, and when it hits the little target thing, this entire object rotates. It rotates back, and when it rotates back, that's when it triggers the release for the dunking booth, right? So the reason I bring this up, Max, shut up, dog. Right? The reason I bring this, so the reason I bring this up is that when this thing gets hit, it starts to rotate. It's going to pick up some angular momentum, right? Because originally it wasn't rotating. It had an angular momentum of 0. Afterward, it was rotating. It has an angular momentum that's not 0. But that begs the question of, where did that angular momentum come from? Because we said that angular momentum is conserved. And if I've got angular momentum after this thing gets hit by the baseball, that means that there should have been angular momentum prior to the baseball hitting the thing. And obviously, before this guy got hit, it wasn't moving, so it didn't have any angular momentum. And here's my baseball. And my baseball, it's not rotating. It's traveling in a straight line. So how does this have angular momentum? So that's pretty weird. And now you might think that, aha, when you throw a baseball, the baseball spins end over end. And you might think, aha, maybe the angular momentum is coming from the spinniness of the baseball. But that's not quite it, right? It ends up being more complicated than that. And instead, we're going to have to figure out angular momentum in a different sort of way. Something else that I'll point out. How much this thing rotates is going to depend on where the baseball hits. What if I were to throw this baseball and have it be off target? What if instead of hitting the target way out here, it comes in and it thwacks this thing right there at the hinge? So here's my little target. If the baseball comes in and hits out here, the pen will rotate. But if the thing comes right here and hits my fingers, it might push my fingers back, but it won't cause any rotation. So if this baseball has angular momentum, and it does, then apparently the angular momentum is going to be different if it hits out here than it would be if it hits right there. So we need a different way of defining angular momentum, because the way we've been defining it, I times omega, doesn't make any sense, because this guy over here has an omega of 0. So there's an alternate way of defining angular momentum. And it turns out that those two methods are, at the end of the day, they're equivalent. But which definition you use is going to depend on what sort of problem you're dealing with. And I'm going to sort of motivate this the same way we motivated, this definition of angular momentum, and that's by analogy, right? We said, aha, to come up with this, I just took the regular momentum and I just said, aha, I'll replace m with I and v with omega, because these are the linear versions and these are the angular versions. But there's another place where we sort of compared linear variables to angular variables, and that was with kinematics. If you recall, if I was moving around, let's say I have an object that's rotating from here to here, this little dotted line distance there, that was called the arc length S. S was equal to the change in angular position times r. So I just take this angle times this distance, and that would give me that distance there. So to get a linear distance in meters, I just took the angular distance in radians times r. The angular velocity was related to the linear velocity, because for v, it was going to equal omega times r. I took the angular velocity times r and got the linear velocity. For the acceleration, the tangential acceleration, well, that was just the angular acceleration, alpha, times r. So you'll notice in each of these three cases, I'm going from an angular variable to a linear variable just by multiplying by the moment arm, r. Let's do the same trick. Let's assume that I can also define my angular momentum a different way. I can say that L is going to be my linear momentum, P, times R. Now, here's where I got to be careful, because each of these things here I was doing as a scalar, but P is a vector, and I want to keep track of the direction. And so what I don't want to write is P times R, because I got to multiply my vectors like vectors. So I'm actually going to write it as R cross P. And again, that shouldn't be super surprising because when I did torque, it was R cross F. So notice even here I'm getting an angular variable by multiplying by R. I'm doing the same deal over here. So P times R, I'm getting L.
What is before that equation, R times F?
That is the symbol tau for torque. It looks like a little scripty T, but it's not a T. It's a Greek letter tau, and I die inside every time you call it something else. Does that help? So,
Yes, thank you.
so L is a vector, and that means that we'll be able to figure out L, but we're going to have to obey the right-hand rule all over again. Yay! It also means that if I want to find just the magnitude of L, remember when you do cross products, it's the magnitude of R times the magnitude of P. But what is P? M times V. So it's R times M times V times the sine of the angle between the R vector and the P vector. So if I define angular momentum this way, when my baseball hits the target out here, you can see that I have angular momentum. Because what's going to happen is this guy comes in, it's got a certain mv, right? Because it's definitely moving and it definitely has mass. It's striking out here, so R is that vector. And since mv is to the right and R is downward, the angle between the momentum and R is 90 degrees. The sine of 90 degrees is 1. That's good. So I'm definitely going to get something. How much angular momentum will I have? It'll be R times M times V. And I can even figure out the direction of my angular momentum. Because for that, I have to use the right-hand rule. And again, to remind you of the right-hand rule, you take your right hand, you stick your fingers in the direction of the first vector. And notice I wrote R times P, not the other way around. So I'm going to start with my fingers pointing down. Fingers pointing down. But now I want to bend my fingers in the direction of P, but P is to the right. So my fingers are pointing downward. I got to bend my fingers the other way, so I have to rotate my hand. And my thumb will point in the direction of the product. So in this case, my angular momentum vector points straight up out of the page towards the camera. Now, what does that mean? Well, just like with torque, if your thumb points a certain direction for angular momentum, the object's going to rotate in the direction that your fingers curl. And lo and behold, if I have an angular momentum that points up, this guy over here is going to rotate counterclockwise, which is exactly what it's going to do. It's going to spin counterclockwise. So having an angular momentum vector that points in a certain direction is related to having an object spinning in that particular orientation. And this will come back again if you guys take physical chemistry with Dr. Coolbaugh, or God help you if I have to teach it again. What you're going to find is that we talk about the angular momentum of electrons in a molecule all the time. What kind of angular momentum does an electron have? Well, electrons can be spinning around the nucleus, so they have an angular momentum. If this is like the nucleus and this is your electron, and we're treating it like a little planet going around the sun, which it doesn't really, but whatever. You know, it's got what we call orbital angular momentum because it's going around the nucleus, plus the electrons have spin. So they're spinning kind of like, it's almost like they're spinning on their axis. That's called the intrinsic angular momentum. And this is going to be like super, super important for all kinds of stuff. So it's important that you have this concept sort of in mind. That's where it comes from. And if I wanted to figure out, say, what speed the swivel was going to rotate at, well, it's going to depend on where I hit. If I hit out here, my final angular momentum is going to be r times m times v times the sine of 90. And obviously that is going to give me all kinds of angular momentum in my baseball. If, however, my baseball strikes right here at the swivel, I just made r equal 0, which is why when I strike there, the thing does not swivel. Relative to that location, this ball has no angular momentum, but this one does. It also matters what direction I hit, because what if, here's my swivel. What if the baseball comes in from that direction and strikes here? Well, now what's going to happen is R is that direction, V is that direction. The angle between R and V is 180 degrees, but the sine of 180 is 0. So I would get absolutely no motion from that. And so you could use both this formulation of angular momentum and this formulation of angular momentum together at the same time. If I wanted to solve this problem, I could say, aha, if the baseball hits the target and stops dead, then what's going to happen is my starting angular momentum would be his L, which is R times M times V. My final angular momentum would be him stopped and him moving, so I times omega. And I could solve for the final omega of the swivel if I knew what I was for the swivel. So you could use both these formulations at the same time if you felt so inclined. Yay, super awesome. Now, one last little bit about angular momentum that we're going to have to deal with. It'll be important, again, if you take higher level chemistry courses where you deal with this stuff all the time. And that's the idea of how do I change the angular momentum of an object? And again, we're going to argue by analogy. Because what we found with linear momentum was that the rate of change of your linear momentum was your force. This is actually how Isaac Newton originally defined forces in his original book. This is called the impulse momentum theorem. We talked about it in chapter 8. But just like forces can cause momentums to change with time, I can also say then that torque can change angular momentum with time. Pretty cool. So, in order to make sense of what this is telling me, because this is actually going to tell me some cool stuff, I want to think through a problem that we're not going to do like the number crunchy math bits on. I want you to understand it conceptually, but doing the math is a pain because it's all three-dimensional and it's really hard to visualize. But you've probably noticed it. If you ever played with a top or a gyroscope as a kid, if you take a top or like a dreidel, if you're Jewish and that's kind of your bag. If I was smart, I would go figure out. A friend of mine is Jewish, and he gave me a little toy dreidel for Christmas, Hanukkah a few years ago. And I have a bag somewhere with one in it. I'd pull it out. It would make a great lecture demonstration, but I don't know where it is. But you take a top, and usually what happens is they're sort of pointy at the bottom, and you spin this thing up here, and you cause it to rotate. And what happens is, while it's spinning, the top, it doesn't fall over, right? It's like it's defying gravity, and it doesn't drop. However, as the thing slows down more and more and more and more, over time, what's going to happen is it'll topple over. But while it's getting ready to topple, it does something really cool, right? The thing they call it is precession, and then we say that the top precesses. And what's going to happen is, it starts off, your top is spinning around and it's standing pretty much straight up vertically. But as it starts to lean over, right? So here's your spinning top, and it's starting to kind of lean over. What happens is your top will wobble around. It's spinning on its axis, but it's also spinning around a point. And usually it'll go faster and faster and faster and faster until finally it lays down flat. Do you guys know what I'm talking about? Have you played with these things enough that you can sort of visualize what's going on here? Because what I want to do is figure out what's up with that precession and why does that precession occur. And the Cliff Note answer is that it happens because I have a certain amount of angular momentum, but there's an external torque acting on my top that causes the angular momentum vector to change. And so the amount of change I get depends on how big that torque is. Now, to see how that's going to work, imagine that my top is sitting straight upright and it's spinning around an axis that runs straight down here through the middle. Now, what are the forces acting on that top? There should be two of them. One of them is a normal force from where the bottom of the top touches the table. That points straight up. The other one is a force of gravity, and that force of gravity should act at the center of mass, which, assuming that my top is homogeneous, should be somewhere along that line. So if my top is well and truly sitting perfectly straight up, then what's going to happen is I've got gravity acting along that axis, I've got the normal force acting along that axis, and I want to think about two things. One is, what torques do I have? And two is, what angular momentum do I have? And the angular momentum part is easy because my top is spinning. In this case, it's spinning, let's say it's spinning around like so. The angular momentum is going to be, if I take my fingers on my right hand and I curl them around in the direction that it's spinning, L points in the direction of my thumb. So right now, when my top is spinning upright, my angular momentum vector points straight up, away from the ground. And right now, how much torque do I have? Well, there's two ways this thing can rotate. It can rotate around this axis, which it is, and there's no torques there as long as there's no friction. The other way that it could rotate is that the top could attempt to topple over one way or the other. But that would be rotating around this axis. And if that's the case, the torque created by the normal force is zero because the normal force is exerted right there at that axis. So no torque from N ever. But gravity, however, is different. Now, if my top were perfectly balanced, and I mean perfectly balanced, so that mg was directly above the place where the top is touching the ground, then even after the top stopped spinning, it could still balance there because the torque R cross F, which would be R times F times the sine of theta, would be zero for that force. Because even though R is this distance here, that's not zero, and F is mg, that's not zero, the angle between R, which points straight up, and gravity that points straight down would be 180, and the sine of 180, totally zero. So if I did have it balanced perfectly, I could imagine balancing it on its tip. Unfortunately, if I'm off even by a smidge, even like 1/1,000,000th of 1 degree, one direction or the other, then what's going to happen is I'm going to get a tiny little non-zero torque from this guy. And that's why I can't balance a pen on its tip. In principle, you could. If I could get the center of mass to be directly above the tip of the pen and let it go, it would balance. But the problem is, if I'm off by even a millionth of a degree, one direction or the other, then what's going to happen is there'll be a tiny torque one direction or the other, and it'll topple in that direction. And so if you have something, you're trying to balance something on its very, very point, it's super, super hard because you've got to be super, super exact, and it's almost impossible to be that exact. So what's going to happen is eventually this thing's going to start to topple one direction or another. But what happens later on if my top is starting to rotate So now what's happening is it's spinning along its axis, but it's also rotating along that point, right? It's trying to rotate this direction as well as spin. Well, now what's going to happen is I've still got two forces on it, the normal force here and gravity there. And what's going to happen is now this force of gravity is going to generate torque around this axis. And to see how, R is going to point up and to the right. Gravity points straight down. And there's my sine of theta, and it's no longer going to be 180 degrees, right? That's going to be a non-zero number when I take the sine of that angle. So I'm getting some torque around this axis if I'm off center by even a little bit. And that is what causes the thing to want to rotate like so. It's why the thing wants to topple to begin with. However, when it's slanted like this, my angular momentum vector, L, points up and to the right. And what's going to happen is the torque that I'm generating is going to cause L to change. It won't be spinning along this same axis because of that torque. And what I'd like to do is to figure out what change I'm going to get in L, but the change in L is going to be in whatever direction the torque is pointing in. So what direction is that torque pointing in? Well, again, I'll do the right-hand rule. I'll put my fingers in the direction of R, which is diagonally up and to the right. But then I'm going to bend my fingers toward the bottom of the page, which means I got to rotate my hand like so. My thumb points into the ground. So right now, this gravitational force is creating a torque that points into the page. And a torque that points into the page makes a thing want to change, or the change in L is going to be in that direction. It's going to be into the page, which means a little bit later, my angular momentum vector is not going to point purely this way. It's going to point a little bit into the page. So what's happening to my object is that when mg is straight down, the torque is this way, and L changes like this. But now there's a mg straight down, the torque is this way, L changes like this. And so what happens is this torque causes the object to rotate around. You get that weird precessional motion, and that's why you see tops, as they start to fail, they swirl around on your axes. Now, again, why do you care? It's really cool. We understand what my stupid childhood toys are doing, but why would I care about this as like a grown-up who doesn't play with tops? Well, two reasons, right? Reason number one is this can explain a lot of things on, like, say, a macro scale. True story. When let's say you have like an object that's orbiting the sun, right? It's going around the sun. It's spinning on its axis. It has a certain amount of angular momentum going around the sun. And then what happens is, as it moves around its orbit, it comes close to another planet. Like, let's say that, our planet comes closer to Jupiter than it was normally. Jupiter's got a lot of gravity. It's a pretty big planet. And what happens is that gravitation can exert a torque on your object, and it can disturb the orbit. It can cause your angular momentum to change ever so slightly. And we see that here in the Earth. Turns out that the Earth rotates on its axis, but its axis of rotation has a certain amount of wobble to it. Right? In other words, what's going to happen is, if you're looking at the Earth spinning on its axis, here's the planet Earth. And normally, if this is like the plane of the solar system, the Earth is going to spin on an axis that is slightly angled. I believe at present, if this is like straight up and down, I want to say this angle is like 11 degrees, but don't quote me on that. And that angle is important because it's this angle that gives rise to things like seasonal changes. right? Summer and winter happen because this angle right here is non-zero. If the Earth rotated around this axis, there would be no summer and winter. It'd be the same kind of weather all year long. But what's going to happen is if the sun is coming in from this side, when the sun is on this side of the Earth, it's summer up here because they're going to get more sunlight, and it's winter down here where they're going to get less sunlight. But then when the Earth rotates around on the other side of the sun, well, now what's going to happen is when the sunlight's coming in from the other side, it's summer down here and it's winter up here. That's why that when it's winter here in the northern hemisphere, it's summer in Australia, and when it's summer in Australia, it's winter here, right? It's their seasons are reversed. They have, Christmas in the summer. It's crazy. But that comes from that angular wobble. And what can happen is as the Earth is gravitationally perturbed by other planets, that angle can change slightly. And that can have all kinds of climate impacts that are measurable. So, yay, it's kind of cool. We can understand even large things using the same kind of process. You can also understand a lot of things on a micro scale using the same sort of process. Again, a big part of what you'll be doing in physical chemistry is you'll be learning about the angular momentum of your electrons, and that's going to give rise to different shaped orbitals. Why are p orbitals funky, weird dumbbell shapes, but s orbitals are round? Well, it turns out that s orbitals have zero angular momentum and p orbitals do not, and that's important. So, this same sort of reasoning can work both, on a macro scale and on a micro scale, as well as normal regular scales. So not a whole lot I can do in terms of making you guys solve problems with this sort of process, but I'd at least like you to understand where procession comes from, because that concept is a useful one. All right, any other questions? All right. So don't forget, the exam is due tonight at midnight. Several of you guys have already taken it. Some of you probably even took it without cheating. Some of you definitely did cheat, and we'll be having some discussions about that. So please remember, it's open book, open notes, but please don't go to external sites, and it's not a group project. Don't work together. You're on the honor system here, but please let me trust you. Do your best. Let me know if there's any issues, and I will talk to you guys tomorrow.